All right, thanks everybody for tuning in. First, I'd like to thank those who funded this work and then a few folks who also contributed to the work technically. As a bit of background, persistent cold air pools, or PCAPs, can cause high particulate matter concentrations during wintertime along the Wasatch Front, oftentimes leading to violations of the federal air quality standards. The high PM concentrations are largely due to buildup of ammonium nitrate, which is formed secondarily from emissions of NOx and ammonia gas, as well as the buildup of carbon-based species, which are largely from smoke emissions. For regulatory and planning purposes, UDAC applies a photochemical model to assess PM2.5 and to project PM to future levels. That model underpredicts ammonium nitrate due to a lack of ammonia entering the system. So UDAC applied a blanket ammonia emissions increase to help to alleviate the underpredictions. But this blanket emissions increase introduces a major model uncertainty that could affect accuracy of projected PM2.5. Our work here focused on investigating causes for the modeled ammonia shortfall by looking more closely at the model responses to chemical and physical processes and investigating potential underestimated or missing sources of ammonia emissions. As part of our study, we reviewed emission inventories and compared them to measured ammonia concentration patterns from the WAFCO study. We investigated modeling uncertainties and deficiencies, particularly with respect to ammonia nitrate formation. We also reviewed scientific literature related to modeled ammonia emissions from vehicles. Based on our investigation, we updated the model and reevaluated base year and attainment year modeling results. For their SIP modeling, UDAC used CMAS to simulate PM2.5 during a 10-day PCAP event in January 2011 and to project PM2.5 to the 2019 attainment year. Without going into too much detail, CAMAC requires inputs of meteorology and emissions. The meteorology was prepared by University of Utah using WRF. The UDAC prepared emission inputs. The modeling domain is shown here. The purple outline shows a large regional domain encompassing all of Utah and parts of the adjacent states, with grid cells spaced at 4 kilometers. And within that, we have a higher resolution domain with grid cells spaced at 1.33 kilometers that encompasses the region along the Wasatch Front. Let's dive into the results of the UDAC base year modeling. Here we have two bar charts showing 24-hour PM2.5 concentrations at two monitors on January 7th, which is the day with the highest measured concentrations during the episode. At Hawthorne Monitor, located just southeast of Salt Lake City, observed PM2.5 and components, shown in the bar on the left, are compared to modeled PM2.5 and components on the right. Here we can see an underprediction in total modeled PM2.5. Looking at the individual components, the underprediction is attributable to nitrate and some sulfate and ammonium. I'll also point out that chloride, although it has a small contribution to the total, is also underpredicted by the model. Similarly, at the Linden monitor, which is located just north of Provo, total PM is also underpredicted, mostly due to a lack of ammonium. And so we began to dig into the physical emissions and chemical processes that might affect ammonium concentrations. Ultimately, we wanted to try to improve model performance without having to include the blanket ammonia emissions that we discussed earlier. Not mentioned here, as a first step, we removed the blanket ammonia emissions from the modeled inventory. Any test shown in blue font means we retained the modification for the final model. The first test was to modify the vertical mixing in the model. We reduced the amount of vertical mixing to a value consistent with similar modeling exercises, and this led to improved simulated PM and gas concentrations. This also narrowed the gap in the ammonia shortfall, so we retained this modification. Next, we looked at bidirectional ammonia surface exchange to test whether the re-emission of already deposited ammonia could be a source of the ammonium shortfall. In essence, the model removes ammonia from the atmosphere via deposition to the surface. and processes were added to CMAS to allow for that ammonia to be re-emitted. So we turned on this process, but it turns out that the snow cover actually squelches the re-emissions of the deposited ammonia. In fact, the snow cover enhances ammonia removal during the daytime when the snow starts to melt. Next, we explored potential shortfalls in the emissions inventory. We found scientific literature that supports a roughly 2 times increase in ammonia emissions from gasoline vehicles. We also found literature supporting a 40% increase in ammonia emissions from cold weather startups. So we scaled the on-road mobile emissions inventory based on this research, and model performance improved. In addition to investigating ammonia emissions, we explored whether the remaining NOx underprediction affects PM2.5. To test this, we increased the NOx emissions by 20%, which actually resulted in lower ammonium nitrate. In other words, the system is highly nonlinear, and a lack of NOx emissions is likely not a source of the ammonium nitrate underprediction. The first chemical process we looked into was the inorganic chemistry. We used an alternative PM chemistry mechanism and found no significant impacts, so this model is not likely the source of the ammonium shortfall. Next, we looked at halogen chemistry. You'll recall that the model underpredicted particulate chloride. Halogens can also enhance oxidation and as a result lead to increases in other secondary PM components. So we artificially increased the concentration of chlorides in the model. Although this helped increase particulate chloride, this resulted in negligible effects on ammonium nitrate and total PM2.5. We also increased the snow albedo to levels observed in field campaigns. The idea is that increased albedo would result in higher photolysis rates and enhanced formation of secondary PM. The increase had small effects on PM2.5, but we kept this change in the model since it more accurately reflected observations. Finally, we looked at cloud chemistry and whether cloud over predictions impact PM2.5. We removed clouds completely as a bounding test case and still found little photolysis sensitivity. Not only that, but fewer clouds led to decreased sulfate, which we did not want. So we incorporated these modifications into a revised model. The chart on the far left is the same that we looked at before, showing monitored and modeled PM2.5 on January 7th. Just to the right is the same chart, but with the revised model results. Most notably, the revised model agrees more closely with observed total PM2.5. This is especially true for inorganic compounds. If we look at linden, we also see improved agreement with total PM and some increases in inorganic compounds. We do still see some relatively large errors, but mostly for species that have a relatively small contribution to PM2.5. As a final step, we use the revised model to project PM2.5 to 2017 and 2019 using UDAC's projected emissions inventory. The table shows each monitor along the Wasatch Front, the base year design value, and future year design values based on UDAC's model and our revised model. You can see that the future year design value didn't change all that much between UDAC and our model, and all sites attain the federal standard at 35 micrograms per cubic meter. Based on our investigation, we identified and revised some key processes in the model to improve model performance and remove the blanket ammonia emissions from the modeled inventory. We found that the model responded well to increased ammonia emissions from gasoline vehicles, and that scale-up was supported by scientific literature. For comparison, UDAC's ammonia injection added 65% to Salt Lake County emissions from an unspecified source to match recent field measurements, while the ammonia scale-up in this investigation added less emissions, around 40%, and from a known deficiency in an emission source. With that emissions increase and changes to the chemical and physical processes in the model, we improved ammonium nitrate performance and total PM2.5, particularly in urban areas. Based on USU's WAFCO study, Ammonia was simulated well, and sulfate also compared well to observations. However, consistent with other modeling in the western U.S., nitrate is still underpredicted. We also found that carbon remained overpredicted. Carbon emissions in the region are largely from smoke, and how those emissions are split into detailed organic, inorganic, and elemental components prior to being input into the model may need adjustment. Also, the model continued to underpredict PM2.5 at rural sites. These are sites where agricultural ammonia sources are important but possibly underrepresented or even missing from the model. And we just mentioned in the previous slide that the projected PM2.5 design values using the updated model were similar to UDAC projections. The revised modeling also tells us that the basin is in a NOx disbenefit condition during these events because the air has lots of NOx compared to oxidants. In other words, NOx emission reductions can raise oxidant levels and, as a result, raise secondary PM formation. Because the system is highly nonlinear, this has implications for accurately projecting PM2.5 based on anticipated changes in emissions. Finally, modeling shows that the basin is close to a balance between ammonia-limited and nitrate-limited conditions as related to ammonium nitrate formation. In this case, the model is in agreement with recent field studies. But there are still some important model uncertainties and biases that could affect how PM2.5 responds to changes in emissions. So, it is still important to try to resolve the remaining uncertainties. Based on these conclusions, we've provided some recommendations for future modeling. First, we recommend modeling a more recent PM2.5 episode, and the new modeling should also incorporate the key updates we've identified in this project. We didn't discuss meteorology in much detail here, but these MET simulations are obviously very important in predicting PM concentrations during a PCAP. So we recommend investigations into potential improvements in these MET simulations. Regarding the emissions and how the inventory is spatially allocated in the model, based on our review of the inventory and findings from the WAFCO study, we recommend improvements to emissions from livestock and landfill sources. We also recommend further investigation into the NOx and chloride underpredictions, the chemical speciation for wood smoke emissions, the role of snow in the surface atmosphere ammonia exchange, and finally, the impact of all updates on PM2.5 responses to future or alternative emission scenarios. With that, thank you all for your time.